Dear students, welcome to this lecture. My name is Mohammad Alamgir, your course instructor of physics. Today I will talk about one of the most famous partial differential equation, which is one-dimensional wave equation. And the focus of this video is actually just on deriving the wave equation. This shows up in a lot of different engineering, physics, and science applications. And the picture that goes along with it, or at least one of the most common applications where I think is the easiest to physically understand that where this equations comes from. So let's begin. When a wave passes through any element on a stretched string, then the element moves perpendicular to the direction of the wave. Yes, I'm talking about the transverse wave, in which element moves perpendicular to the direction of the wave, as we can see here in this twig. And by applying Newton's second law to the element's motion, we can derive a general differential equation which is called wave equation, and that governs the travel of any type of the wave. Here we'll derive a general differential equation by applying Newton's second law, which will govern the travel of the any type of the wave. Dear students, to derive the general wave equation, we have to analyze a string element, as we can see here in this fig. Let the string element has mass dm and length L, and as a wave it travels along a string of linear density mu, which is stretched along the horizontal x-axis. And let us assume that the wave amplitude is so small that the element can be tilted only slightly from the x-axis as the wave passes through it. So we can observe a slight tilt here. Also, we can see here the two forces F1 and the F2, which are acting on the left and the right ends, are producing an acceleration having a vertical component AY. Here it is, directed in the upward direction. The force F2 here on the right end of the element has a magnitude equal to the tension T in the string and is directed slightly upward. Also, the force F1, here it is, which is on the left end of the string element, it also has the magnitude equal to the tension T in the string, but it is directed slightly downward. And both of these forces causes a slight curvature of the element. And due to this slight curvature, these two forces are not simply in opposite direction to cancel each other. Instead, they combine to produce a net force that causes the element to have an upward acceleration, which is AY. Here it is. Now by applying Newton's law to all of these y components, which is Fy equals to MAy, as both of these two forces are in opposite direction, so we can write the net force as F2y minus F1y equals to dMAy. Now we are going to analyze the equation from the string element. That first we shall analyze the mass dm, then the acceleration component ay, and then the individual force components F2y and F1y, and finally the net force on the left side of the equation. Now here first we analyze the mass of the string element. As we know that linear density is mass per unit length of the string. So we can define the mass in terms of the linear density and the length L by this definition, which is dm equals to mu into L. Here mu is the linear density of the string. Also, we can see here in this fig that this length of the string element is slightly tilted, which is approximately equals to this length dx. So here we can see that the length is approximately equals to the length dx, and we can replace here in this equation L by dx, and we can write it as dm equals to mu into dx. Now we'll discuss the acceleration. As we know that acceleration is the second derivative of the displacement with respect to the time t. So here in this case the particle motion is along the y-axis, so we'll take the acceleration as the second derivative of the displacement y with respect to the time t, and we can write it as a equals to d square y by dt square. Now we'll discuss the force F2. As we can see here in this fig, the string element, and F2 is a force which is directed slightly upward at the right end of the string element. So we can see here the force F2 which is shown in this fig, and it is divided into its component, and we can see here F2x is along x-axis and F2y is along y-axis. So F2 is divided into its rectangular component here, and if we denote this slope S2 at the right end, and we relate it with the component of the force, so we can write it as S2 equals to F2y divided by F2x, as we can see here in this equation. Here it is. So we can also relate the force with the tension T, as we know that the magnitude of the force is basically equal to the tension T in the string. So we can write here F2 as magnitude of the F2 which is equals to the F2x square plus F2y square and whole square root. And then we'll replace F2 by T, which is tension T in the string, and we have discussed it earlier that tension T is basically equals to the magnitude of the force F2, and here we have replaced T with F2, and T is equals to the magnitude of the force which is equal to the F2x square plus F2y square and the whole square root. Look at this. As we can see here, this string is slightly tilted here. So the component of the forces, which is F2x and F2y, we can see here. F2y is much smaller as compared to F2x. Also, as we have discussed in the previous slide, the magnitude of the force, which is F2x square plus F2y square whole square root. Here it is. Also, we have discussed it that magnitude of the force is equal to the tension T in this string. So we have replaced here the magnitude of the force F2 by the tension T here. And finally, the equation F2 equals to square root of F2x square plus F2y square. As F2y is much smaller than F2x, so we neglect F2y. And by neglecting F2y from here in this equation, we have the final equation as tension T equals to F2x. Because here the square of F2x will be cancelled by the square root, and finally the equation will have T equals to F2x. Also, by substituting this value in the equation of the slope, which is S2 equals to F2y divided by F2x, here by replacing the value of F2x which is equal to the tension T, we'll get the equation F2y equals to tension T into S2 slope. As we have analyzed the force F2 on the right end of the element of the string, so we'll get the equation F2y equals to tension T into S2. Similarly, the same analysis on the left end of the string element will give us F1y equals to tension T into S1. As we have analyzed for the mass and got the equation which is dm equals to mu dx. Here dm is the mass of the string element, mu is the linear density, and dx is the length of the string element. Also, we have analyzed for the acceleration along the y-axis direction and got the equation as ay equals to d square y by dt square. Then we have analyzed for the forces along the right hand and along the left hand, which is directed towards the y-axis direction, and got the equation as F2y equals to tension T into slope S2. S2 is the slope on the right hand of the string element. Also F1y, which is equal to the tension T into S1. Here it is the force which is directed on the left hand of the string element, and S1 here is the slope on the left hand of the string element. And then net forces, as we discussed, which is F2y minus F1y equals to dm into ay. Now by inserting all of these values into this equation, we get the equation as ts2 minus ts1 equals to mu dx d square y by dt square. Now dividing this equation by t and dx, then we get the equation as s2 minus s1 divided by dx equals to mu divided by t into d square y by dt square. Here the difference of the slope s1 and s2 is only the small differential amount ds, and s is the slope at any point of the string element. And we can write s equals to dy by dx. Also, we can replace s2 minus s1 with ds, and we'll get the equation as ds by dx equals to mu divided by t into d square y by dt square. Here it is. Also, as we have discussed that s equals to dy by dx, so here putting the value of s, will get the equation as d into dy by dx divided by dx equals to mu divided by t into d square y by dt square. And then finally we have the equation as partial square y by partial x square equals to mu divided by t into partial square y by partial t square. Here is the final equation, which is partial square y by partial x square equals to mu divided by t into partial square y by partial t square. In this last step, we switch to the notation of the partial derivatives. This is because on the left we differentiate only with respect to x, and on the right we differentiate only with respect to t. Also, in previous lecture we have discussed the dimensional analysis and got the equation v equals to square root of t divided by mu. Now by inserting this into this equation, we'll get the final equation as partial square y by partial x square equals to 1 over v square partial square y by partial t square, which is the final wave equation. And this general differential equation governs the travel of all types of the waves. At the end, I'm very thankful to all of you for being here with me. Dear students, if you have any question or any concern regarding this lecture, you may directly contact to my WhatsApp number, or you may comment here in this YouTube video. Stay safe, stay blessed, have a great day.